Hello. So, title of our project is Designing a UAV-ready sensor package for rapid deployment during volcanic crisis. This is a collaboration between myself and Dan Peters at RAL Space, John Francois at the University of Oxford, Kunja Liu at Loughborough University, and Stefano Rolfo at Scientific Computing Department. And our SAQN mentor for this is Jim Mills. Next slide, please. So the reason we're doing this, erupting volcanoes emit a mixture of air quality pollutants such as gas, ash, and aerosols, and these can cause health hazards for the local communities. What we're particularly interested in is particulate matter, so the ash particles, and sulfur dioxide. And volcanic activity can be difficult to predict and can have rates of emission which change quite rapidly. So next slide, please. If we can mount sensors on a UAV, an unmanned aerial vehicle, this could give us a means to track volcanic plumes as they travel. Our aim is to make a sensor package that could be deployed to a developing eruption and give us this capability to track plumes and validate models of plume dispersal, and to use that to support public health decisions for the local communities, so by improving that tracking and modelling of the dispersion of the plume. But we'll also build this capacity within STFC to monitor pollutants during other times of crisis as well. So this could be used in volcanoes, but it could also be used, for example, on a plume from a fire or an industrial plume. Next slide, please. So there are a number of challenges to working with UAVs, which mean we need to design our package specifically for this application. So we need to have a package that is lightweight, small in size, and draws little power. We also have the challenge of trying to get unbiased sampling of particles in a moving airflow. Working with UAVs is something that we have a bit of experience with at STFC. So we have several UAV models that we use in RAL Space that have been deployed previously for applications such as crop health. But this will be a new instrument that we make that will help us build capabilities within our UAV facility. Next slide, please. So we're looking to design an instrument that can be used on UAVs similar to the two that are shown in the pictures on the right. So these are lightweight fixed-wing UAVs that are battery operated. So you can't see the scale on these, but the wingspan of each of these is about 2 meters across. So it's important that we use these fixed-wing UAVs because they have a longer range, which is important as we don't want to get too close to the volcano. But also, perhaps most importantly, you might have seen multi-rotor UAVs like quadcopters in common use, but the fixed-wing UAVs like we show here, it makes it easier for us to get the sensor away from the influence of the rotors. So we would try and project it out the front of the UAV in front of the propellers so as not to be influenced by them. We're also looking to these lightweight, low-cost UAVs because they're easier to fly and easier to purchase. Next slide, please. So that imposes several constraints on us. So for this class of UAV, the payload weight is typically a maximum between 600 and 1,200 grams. Ideally, we don't even want to push towards this. We want to keep the weight as light as possible because any extra weight will reduce the flight time and the range of the UAV. The payload bay volume is generally about 1 litre, so that's not incredibly much space to fit all of our instruments into. And we need to be able to power this instrument for the duration of a flight. Next slide, please. So to do this, we'll try and combine cheap commercial off-the-shelf sensors Those will be a particle counter, electrochemical sensors for sulfur dioxide and hydrogen sulfide, and a sensor for carbon dioxide. This is particularly useful in volcanology because it's common to look at the ratio between sulfur dioxide and carbon dioxide. So these sensors are quite small and quite lightweight. They might only weigh tens of grams, so ideal for this application. But the full sensor package will need to combine several of these sensors along with the readout electronics. So that could be something like a Raspberry Pi and a microcontroller for overall control of the sensors, and some form of telemetry or storage to get the data back. Next slide, please. And sampling particulates from a moving platform can be quite complicated. So we want to try and get isokinetic or close to isokinetic flow into the sensor inlet, which means essentially that the streamlines of the flow into the sensor are not disturbed when they enter the sensor. So if the flow into the sensor is bent sharply, then the inertia of large particles means that they're likely not to be taken up by the inlet. And that's something that we want to avoid to try and minimize the bias in sampling. This is why, another reason why we need to use a fixed train UAV, is that we expect the motion to be at an approximately constant speed relative to the surrounding air. And we'll be looking at using 2D CFD modeling to help us determine the best configuration for the sensor and the inlet aboard the demonstration airframe. So if you look at the image below to the right, this is essentially an airfoil that we can model in 2 dimensions, and that should enable us to get a good picture of where our sensor needs to be. Next slide, please. So the next steps, we're still in a relatively early stage of the project with much of the work still to come. So the design and prototyping will be carried out in the coming months. And we aim to have the sensor package assembled by May, and we should do some testing of this both in the lab and hopefully in the field before the end of the project in June in a representative environment. So thank you.